I'm going to present the study of simulating the pathogenic spreading of misfolded alpha-synuclein in Parkinson's disease. So Parkinson's disease PD has been suggested as a prion-like disease often associated with progressive accumulation of misfolded alpha-synuclein. It has been suggested that misfolded alpha-synuclein can physically move from neuron to neuron that spread into connected regions, causing further misfolding of endogenous alpha-synuclein. It can also deposit into insoluble aggregates, driving cell dysfunction and neuronal loss. The principal alternative hypothesis for the mechanism underlying PD is selective vulnerability, which suggests that certain neurons, perhaps because of gene expressions, are intrinsically more vulnerable to the accumulation of misfolded alpha-synuclein and becomes dysfunctional and structurally abnormal before the others. Actually, the two mechanisms are not mutually exclusive, and the previous literature has suggested that both of them can account for the spatial distribution of alpha-synuclein aggregates and neuronal loss in PD. So here, using generic parameters extracted from healthy connectome and genetic data, we propose a spread model that integrates the two mechanisms onto the same framework to simulate the spreading of misfolded alpha-synuclein and regional accrual of neuronal loss. So the model takes a susceptible, infectious, and removed setting in which normal alpha-synuclein are susceptible to the infection of misfolded alpha-synuclein, and the latter are infectious, acting as inductive agents causing infection of susceptible alpha-synuclein, and they can get removed by the neuroprotection mechanism, no longer taking an active part in the system. So alpha-synuclein can move along the structural connections determined by connectome, and once an outbreak takes place, misfolded alpha-synuclein will accumulate and deposit into aggregates, driving cell dysfunction and neuronal loss. And in the meanwhile, gene expressions, by controlling the synthesis and clearance of alpha-synuclein on top of will modulate the regional vulnerability to the accumulation of misfolded alpha-synuclein on top of the topological features and the geometrical features of the connectome. So all the parameters used in the model were adapted from a healthy brain. Gene expressions, here we focus on GBA and SNCA expression to control the clearance and synthesis of alpha-synuclein were obtained from Allen Brain Institute. Structural connectivity and functional connectivity were constructed from diffusion and resting state MRI data provided by Human Connectome Project. And PD atrophy map, which measures regional volume change in PD progression, was derived from deformation-based morphometry values estimated from structural scans of PD patients and healthy controls provided by Parkinson Progression Markers Initiative. So the model includes 3 modules to start. In the first module, we sought to estimate the regional density of endogenous alpha-synuclein as the initial condition of the pathogenic spread. So in this module, normal alpha-synuclein can get synthesized or cleared. They can also move into other regions with probabilities proportional to the connection strength. So after the system has reached the stable point, we initiate the pathogenic spread by injecting misfolded alpha-synuclein into the seed region. So in this module, normal alpha-synuclein can also get infected due to the exposure to the infection of misfolded alpha-synuclein. And in the meanwhile, in module 3, the accumulation of misfolded alpha-synuclein will induce accrual of neuronal loss. So the equilibrium solved at the stable point of module 1 reflects regional variations in vulnerability in healthy brain. So basal ganglia is rich in endogenous alpha-synuclein, and substantia nigra has the highest expression level of normal alpha-synuclein, making it highly vulnerable to the infectious attack of misfolded alpha-synuclein. And to identify the epicenter, we also derived spread threshold, a marker of disease extinction and outbreak for each region to measure the plausibility of initiating a major outbreak. And we found that substantia nigra has the lowest spread threshold, supporting the notion that it acts as an epicenter in PD progression. So in the spreading process, we simulated neuronal loss at each time step to see how it fits with the spatial patterning of real atrophy. The system yielded a high model fit at around 2,000 time steps, after which the model fit drops slightly. So, because simulated neuronal loss becomes more widely spread, while the real atrophy was derived from patients of early to medium disease onset. And moreover, the peaking pattern and the peak values of model fit are preserved across networks of binary densities ranging from 24% to 46% and are very robust. We also identified that our spread model, which is integrated with gene expressions to control regional vulnerability on top of the network features of the connectome, has more predictive power than network measures per se, including node degree, strength, and centrality measures. So we next sought to investigate the role of functional connectivity, and we identified that the integration of functional connectivity facilitates model fit at 4 different network densities. So integration of functional connectivity will bias the alpha-synuclein toward regions of more synchronous neuronal activity. But however, excessive influence of functional connectivity degrades model fit, suggesting that a balanced effect of structural connectivity and functional connectivity is required in driving PD pathology. So finally, we sought to investigate how likely it is to observe a model fit in null models. So we first disrupt the spatial embeddings of the brain regions and then rewired the brain network with degrees and connection strength preserved. And we found that both of the procedures significantly reduced model fit. And we then shuffled gene expressions and found that both randomized GBA expressions and SNCA expressions significantly reduced model fit as well. Critically, non-informative uniform transcription profiles, simulations based on non-informative uniform transcription profiles perform better than chance, providing more evidence that GBA and SNCA play an active role in shaping PD pathology by controlling the clearance and synthesis of alpha-synuclein respectively. So the take-home message for today is that based on using parameters extracted from the innate characteristics of a healthy brain, a spread model that integrates the 2 mechanisms, pathogenic spread and selective vulnerability, replicates the spatial patterning of PD atrophy identified from an independent data set of PD patients. And moreover, disruptions of these innate features, these generic parameters, significantly reduce model fit. So our study suggests that PD atrophy results from the interplay between the routes of pathogenic spread and selective vulnerability to the accumulation of misfolded alpha-synuclein. And structural connectivity dictates the moving pattern, the mobility pattern of alpha-synuclein, while functional connectivity bias spreading also improves fit, suggesting that neuronal activity may also drive disease spread. And finally, gene expressions here, GBA and SNCA, plays an active role in shaping PD pathology as well by controlling the clearance and synthesis of alpha-synuclein on top of the topological and geometrical features of brain connectome. So we also visualized a simplified trajectory of the spreading of misfolded alpha-synuclein. So alpha-synuclein will move along the structural connections and they will light up a node once they encroaches on the corresponding region in the brain. And that's all. Thank you for your attention, and thank you for two of my supervisors and all my lab members. And well, I'm very, very grateful for your kind and warm support during the past 2 years. And questions?
Any questions? Oh.
So just to clarify something before I ask the question, so how did you compare, so you said you compared it to patterns of brain atrophy. Is that on imaging, neuroimaging, or is that on pathology, on autopsy specimens?
So imaging.
Okay, and you don't actually include sort of a timestamp of how your model spreads. So at what point did you choose to kind of compare your model to the atrophy that you see? Because when you see in imaging, PD patients can be imaged early in the disease, later in the disease. So did you choose end-stage PD, early-stage PD?
You mean choose the time step of the real atrophy, or you mean?
Yeah, so the point at which you decided to compare the imaging of the PD patients, was it sort of at the end stage when you were looking at more global atrophy processes, or was it sort of middle stage of PD? Because that will obviously influence which areas are atrophied in that disease process.
So the atrophy map was derived from patients' first visit in PPMI dataset, and we compared every data point with the real atrophy, and we found there's a peak, and then the model fit slightly drops. And we argue this is because the simulated neuronal loss in the simulation becomes more widely spread, while the atrophy was derived from patients of early onset.
Earlier stage PD, yeah. And there's no way you can sort of look at synuclein patterns at the end of your model versus sort of autopsy specimens in the Braak staging, because you can look at synuclein spread and you can look at cell loss, and Braak's staging does that, looks at synuclein spread and cell loss, and sometimes there isn't, there's a dissociation sometimes with that as well. So can you compare across the autopsy specimens to see whether the end stage of your model fits that, and whether the synuclein pattern fits the synuclein pattern seen in real brains and the atrophy pattern seen in real brains as well?
Oh, it's a very, very good point. So the atrophy, alpha-synuclein aggregates and neuronal loss are two different aspects of the model. And actually, in our current modeling, we model the neuronal loss as a transformation of the accumulation of alpha-synuclein. And then in our current setting, we compared which one fits better with the real atrophy, and we found that neuronal loss, simulated neuronal loss, has better performance than the accumulation of alpha-synuclein itself. Mm-hmm. So did I?
No, I think so. Thank you very much.
Thank you.
Last question.
Thank you. That was a really, really fantastic presentation.
Thank you.
So I was just wondering if you could talk, maybe I missed it, but if you could talk just a little bit more about how you use the Allen Human Brain Atlas gene expression data to sort of model the regional vulnerability, if you did some sort of probe pre-selection or just used an entire connectome, or how that was done.
So the gene expressions are Z-scores originally provided by Allen Brain Institute. So we use a standard normal cumulative distribution function to convert the Z-score into a value between 0 and 1 as a probability. So in each voxel, there's a probability that normal alpha-synuclein can get generated. And in the same time, it also has a probability of getting cleared. So in this way, gene expressions plays a role by controlling the probability of getting generated and cleared, removed, sort of thing.
Okay, I see. Thank you.
Thank you for your question.
Okay, let's thank the speaker and all the speakers in this session. And this session is concluded.